Hi everyone, welcome to today's seminar. So the talk of today is part of the UNESCO UNITWIN Complex Systems Digital Campus, and it's organized by the Applied Math Laboratory of Le Havre Normandy University. Also the French Society of Theoretical Biology, and also with the help of the Hudson School of Mathematics. And it's our pleasure today to welcome Joshua Epstein from New York University, who will be talking about triple contagion toward cognitive epidemiology.
All right, well, it's an honor to be here and to speak to this distinguished group on a topic that I've been working on for several years. It's really the immediate most recent publication was in the Royal Society, and it's about triple contagion, and I'll tell you all about that. I'm a professor of epidemiology here at NYU. I direct the NYU Agent-Based Modeling Lab, and I have several faculty appointments, including the Courant Institute, where I met Benjamin. The idea of this line of work is to deepen mathematical epidemiology to encompass human behavioral adaptation and its underlying cognitive drivers. And I want to show a family of models today, of differential equation models with behavioral adaptation. First is a model that I called coupled contagion of disease and fear, we published in a few years ago. But this involves contagious disease and contagious fear of the disease. Then there's a model, triple contagion, published in the Royal Society recently, where there's contagious disease, contagious fear of disease, and contagious fear of the control, in this case, vaccine. And we'll talk about how how those two fears play against one another and what consequences it has for epidemic dynamics. But they all offer behavioral mechanisms for multiple pandemic waves. And again, most classical epidemiology, as I'll review, really doesn't talk about behavior, when I think we'd all agree it's quite important, and we need to find simple models that encompass it in some way. All right, so these all offer behavioral mechanisms for waves, and I want to show you a more advanced agent, agent 0, which actually includes some rudimentary cognitive science, some cognitive apparatus, and in particular, a simple model of fear learning, fear extinction, and fear transmission. All right, and then conclude by telling you about some plans to scale this up with Courant on a NSF, large NSF multi-year project. I'm assuming we get that. But let's begin at the very beginning. For those of you who don't know about mathematical epidemiology, and I apologize if everyone already knows this, but it all really begins, modern mathematical epidemiology begins with this Kermack-McKendrick system published in 1927 called the SIR model, because the compartments are susceptibles, infecteds, and removeds. And in this simple model, the idea is simply that there's a flow from the susceptible pool to the infected pool, and a flow from the infected pool into the removed pool, which you could think of as dead or recovered. I like to think of it as dead. But the idea here is that it's a perfect mixing model. Okay, it's perfect mixing because of this SI term, right? The idea is that, you know, SI, why is that perfect mixing? If I lined all the susceptibles up in a row and lined all the infecteds up in a different row, and I had every infected sneeze in the face of each susceptible, just march down the row of susceptibles and sneeze on them, then I'd have S times I sneezes, each one of which is assumed to transmit with some probability beta or some constant beta. So the idea is dsdt, the rate of change of the susceptible pool, is proportional to s times I, and the constant transmission rate is beta. So dsdt falls at minus beta si, but people flow where? Into the infected pool. So that grows by beta si, but all else constant, they flow into the removed pool at minus gamma I. So without any transmission, if we just started with a bunch of infectives, it'd be negative exponential decay. All right, and it's exponential growth of the removed group. All right, so constant population, perfect mixing, and you get these very classical curves. The susceptible curve falls, the infective curve rises because people are transferring from the susceptible to the infected pool, and then they leave the infected pool for the removed pool, okay? And it gave very counterintuitive insights at the time. I mean, it showed for the first time really rigorously that epidemics are threshold phenomena. Why? Because what does it mean to say there's an epidemic? It means that DIDT is positive, but DIDT is beta Si minus gamma I, so that must be positive. Oh, so well, then that must mean the susceptibles exceed the removal rate over the transmission rate, and that the thing dies out otherwise. So it takes off above this threshold and fizzles out otherwise. And the huge implication of this is the idea of herd immunity, that you don't have to vaccinate until the remaining susceptible pool is gone. You just have to vaccinate until the remaining pool is sub-threshold, and then the thing will die out. And the classic result for, this is a classic result for homogeneous and well-mixed populations. And it also gives a nice reason why overly deadly bugs aren't very good at sustaining epidemics, which you can clearly see. If the gamma is so huge, then the susceptible pools, it's very easy to be under the threshold. Okay, and if we recast this in terms of the famous R0, the reproductive number of the disease, we can just rearrange this condition so that the takeoff condition is beta S over gamma greater than 1, or this equation here, R0 greater than 1 is an epidemic, R0 less than 1 is none. And in general, there are fancier treatments where R0 is actually the spectral radius of a certain operator, the so-called next generation matrix. And, if R0 is greater than 0, then the zero equilibrium is itself unstable and so forth. So there are fancy renditions of this, but the basic idea is this, and it gives a very nice formula for herd immunity through vaccination, assuming a perfect vaccine, but obviously easy to multiply this by some effectiveness number. But to get below the threshold, you have to subtract V, the vaccinated fraction, from the initial susceptibles. That has to be less than the threshold. This is not the fraction, it's the number of susceptibles minus the number vaccinated, less than the takeoff threshold. But that can be rearranged to say that you have to vaccinate 1 minus 1 over R0 of the susceptible population, which is a very elegant, pretty back of the envelope formula, I think. And what it suggests is that for the 1918 pandemic flu, which had an R0 of 2, if you'd had a vaccine and were able to vaccinate half the population, the thing would have died out. That's a very nice little result. And if you recall, during COVID-19, before the Delta variant, excuse me, the CDC sought, something on the order of a 70% vaccination rate. So just for the heck of it, how might they have come up with that sort of number? If you assume a COVID R0 of around 3, which was plausible at that time, and a vaccine efficacy of 95%, which was the, how Pfizer was rated, you get 0.67 over 0.95, and it's about 70% of the population should be vaccinated to make the thing die out. And we had all sorts of other departures from this because of vaccine refusal that I'll come back and talk to. But this is some of the basic results of the most rudimentary, well-mixed ODE epidemic models, the classic epidemic model. Okay, a triumph of analytical modeling. Picasso said art is a lie that helps us see the truth. I think that's true of all the best models. And I think for students and for us, it's important to develop an instinct, a sense of smell for the most fertile wrong model. And this is a good example of that. Box said, all models are wrong, but some are useful. And I'll show several other examples of this below. But it gave very important insights, and it also works very well empirically when perfect mixing applies. And there are lots of data sets where, children mix well, and you get a very good fit to the Kermack-McKendrick picture. All right, clear? All right, but there's an important problem with this setup. All right, the problem is, would you keep milling around if you knew there were a plague underway? I mean, I don't think so. I wouldn't. And Poincaré said, the plague was nothing. Fear of the plague was much more formidable. And the classical models just don't include any behavioral adaptation. I mean, quite obviously, they just keep mixing SI, 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 regardless of how prevalent the disease is, which is, kind of stupid and not very realistic. As we see in actual epidemic history, people flee, they hide, they do all sorts of things to get out of the way of the thing. All right. Now, I think most modelers, if you ask, why don't you include behavioral adaptation? They'd say, well, human behavior is too hard. We don't really know much about humans, so we leave it out. But I'm afraid that doesn't fly. You're not leaving it out. You're making a strong assumption that the contact pattern is invariant to the prevalence of the disease. I mean, that's a deep behavioral assumption, and you're making it. So you're including behavior one way or the other. You're just doing it badly. And can we do a little better? So I want to show a couple simple approaches focused on the phenomenon of multiple waves, which of course are also not possible in the Kermack-McKendrick family. SIR, susceptible, exposed, infected, removed, all this entire family of ODE models. You can't get waves in any of them. So here's the lineage I've been developing. We have coupled contagion models that do generate multiple waves by including human fear and human adaptation. And one of these I published in 2008, coupled contagion dynamics of fear and disease, mathematical and computational explorations. And a second we published recently with Jen Crodell, who you might have met at Courant. I also met her when she was a postdoc at Courant and since has gone to Middlebury. But she was at Courant when we all did this work, which is triple contagion. It has two fears, one fear of disease and one fear of the vaccine. And it produces cycles of behavior and disease dynamics. Now in the first paper, there's just a single fear of disease and call that FD. Then the idea is if there are new cases, it makes people afraid. And when they're afraid, they reduce their contacts. But when they reduce their contacts, they suppress the rate of growth of the epidemic. So new cases fall, but this makes them less afraid. And they now come out of hiding and go back into contact. But this pours fuel on the fire in the form of susceptibles and produces new waves of disease. And this is truly what happened in 1918 and in COVID-19 before the vaccine. And I'll come back to this. In the second paper, there are two fears, one of disease and one of the control, which we assume to be vaccine in this case, FV. And now, if there are new cases, it's not simply that F of D goes up, but F of D exceeds F of V. You're more afraid of the disease than you are of the vaccine. And this makes people take the vaccine. But as before, when the vaccine goes up, the new cases go down and can reach the point that the fear of disease is now less than the fear of vaccine itself, and vaccine goes down. And now we get new cases because of low levels of vaccination. And again, this is a different mechanism of multiple waves. And I'll talk about this as historically, smallpox exhibits this very well. All right, so these are the ideas that the cases produce some change in behavior that changes contacts, which changes the course of the disease, which changes the fear, which can produce resurgence. All right, so we'll talk about the details of this. In the first of the papers, coupled contagion of fear and disease, mathematical and computational explorations, there are two interacting contagion processes. One is contagion of disease, which is a particulate viral transmission mechanism, and the other is fear of the disease, which is a cognitive, non-particulate mechanism. And the idea of the model is simply that individuals contract disease only through contact with disease-infected. Individuals contract fear through contact with the disease-infected, sick, or the fear-infected, the scared, and those who happen to be infected with both fear and disease, the sick and the scared. Scared individuals, whether sick or not, withdraw from circulation, which suppresses the spread of the disease. But because new cases are down, the fear decays and people return to circulation prematurely, and this pours fuel in the form of susceptibles on the infected embers that are still circulating, and a new wave explodes. All right, and there are several possible states are labeled appropriately: infected with fear only, infected with pathogen, and so on. And we have several parameters governing the rate of removal from self-isolation and so forth. All right, and it's quite simple. And there's really now two probabilities: one, the transmission probability for the fear, alpha, and a transmission probability for the disease, beta. Okay, and the classical SIR differential equation formulation of this is this. It just looks a little bit complicated, but on close inspection, it really simply subsumes two SIR models. I think of this as a kind of fugue of SIR models. With alpha is 0, you get the classical SIR model for the pathogen shown in these terms. It's minus beta SI, and DIDT is beta SI, and removal is minus gamma I. So here's the classical pathogen epidemic. And if you say there's no pathogen and there's just fear, beta equals 0, you get a pure SIR fear epidemic. Here it's minus alpha SI that goes into the fear infected with fear pool, and they're removed from the infected fear pool at the same classical rate. So it's really two classical models coupled in this model, and removed. People can go back to the susceptible pool. There's re-entry into these other compartments. Okay.
Yeah. So Joshua, there's a couple of questions, but if you can spend more. So where does the fear appear here? So IF, right?
Yeah.
So
IF is the fear. Infected with fear only, infected with pathogen only, so infected with both.
How the big picture goes into your equation? If you can you put the equation again?
Yeah.
So you have the susceptible.
Susceptible to everything.
Yeah. So they have IF is for the fear of the disease only. Of the disease only. Now, here there's only the disease of the fear of the disease.
Yep.
No, the both fear of the vaccine.
No vaccine in this first model.
No vaccine in the first model.
No vaccine. This is the pure. It's the first one where there's only fear of the disease, no fear of the vaccine.
Oh, so people get out of S either by contamination, so
right,
they become infected, or by
choice.
They're infected by fear. So
exactly, and they decide they could be sick, they could be completely healthy, susceptibles, and they go to their basement and zip themselves in until things calm down.
Yeah, interesting. Oh, yeah. And the P means the P means what is the disease?
Pathogen. P is pathogen. F is fear. I apologize. I should have gone much more slowly.
No, that's good. That's good. We can stay on.
So P is pathogen. So and again, P is pathogen. So the IP dynamic is, if there's no fear, it's minus beta I, minus beta SI, just as in the classical model, pathogen only.
Yeah.
And they go into the I pool at beta SI, pathogen only.
So
and they're removed by the natural death rate
That's classic. But is there a perfect symmetry now? Are the two models the same? That was the question, but I wanted to prepare the question.
Not exactly, no.
Not exactly.
It's interesting that they're not.
Okay. All right.
It's interesting that they're
so on the parameters, that's the difference. You will play with the parameters, right? That's the difference.
Well, the other difference is you can return to circulation by this route.
Yes.
You recover from fear and return to the susceptible pool.
Oh, yeah. And that's
which is not possible in the classical model.
Yeah.
You just removed and that's it.
Yeah,
so while it's true that in the pathogen dynamics, you're removed permanently by biology, your immune response.
Yeah.
But in the behavioral one, you can re-enter the susceptible pool.
Yeah.
So they're not exactly the same, and it produces an interesting asymmetry that I'll come back to.
All right. Thanks.
All right. Very good. Very good. Sorry to not, I don't see the chats, so please just barge in and ask me.
All right.
Okay. All right. Good. Yes. So P is pathogen, F is fear, PF is both pathogen and fear. All right. Good. All right. But what we get from this model is, we get multiple waves by this behavioral mechanism. And it's actually, it gives some encouraging correspondence to what happened in the 1918 pandemic flu. Here's what happens in the model. And again, it's obviously parameter dependent, but we're really talking about, existence theorems here. So this starts with a lot of susceptibles. The infection begins under the classical, dynamic. But this produces a lot of fear. And because they're fearful, they go into hiding, which suppresses spread. But now the suppressed spread makes people lose their fear. So the fear extinction plummet, fear extinguishes, fear dies out. But what that means is that people come back into the susceptible pool. They come out of the basement, back into the susceptible pool. But now there's lots of fuel for a second wave of the epidemic. And so this is the picture. Okay? You get a big spike in epidemic, new cases. This produces a lot of fear and isolation. That suppresses the disease. But now people are less afraid. They come out of hiding. This is now pours new susceptibles onto the remaining embers. You don't need a lot of infecteds. You just need a few. And then you pour fuel on them and the thing blows up. Right? So it's really the susceptibles that are driving everything. And you get this second wave. All right? And again, not possible in the classical model. And here's one simple way to arrange that. And, what we saw in 1918 was for all the cities in the UK and Wales and all the US cities, we had these two waves. And so, I thought, well, let's do a big data, as I said before, I'm not so focused on data, but I thought, let's do a big, brave data analysis of Chicago. So I read two newspapers at the time, and this is the Commissioner of Health. The blue curve is the Chicago one. And at the outset, when the thing burst into, big contagion, he said, go home and go to bed until you're well. So the minute the thing took off, he said, get the heck out of circulation. And this indeed had the effect of suppressing the disease. But because they didn't know that it was a threshold phenomenon, and they didn't know the Kermack-McKendrick equations, they didn't know anything about herd immunity, they published, we're practically out of the woods. There's very few infecteds. Practically out of the woods. All bans are off. But of course, they didn't understand that in producing all bans are off, you're pouring fuel onto the thing, and they got a second wave. And this happened in all these cities. So, I mean, again, Einstein said, theory should be as simple as possible, but no simpler. My adage is, data should be as big as necessary, but no bigger. But I'm not, obviously, we're also empirical scientists. And if you want a full analysis, city by city, Neil Ferguson and Bootsma did a beautiful one in PNAS, where they did detailed analyses for each city. And this is very much the mechanism that was at play. All right. You can play other games. Fear, here's where the asymmetry comes in. Fear can dissipate before the infection does. And it can also transmit faster than the bug itself, even when the transmission rates are the same. To your point, Benjamin. It can transmit faster than the bug itself, even if the two rates are the same. Why would that be? Basically, because there are more channels to transmit fear, and it doesn't require physical contact. And we solved for the condition under which fear spreads faster than the disease.
Yeah.
And this is the simple parameter arrangement in which the fear transmission rate has to exceed this crazy looking thing.
There was another question. So since you're talking about that, maybe I think you will answer that during the talk, but how do you estimate these rates for the fear?
Yeah, I mean, these are, I will talk about that.
Right.
And we've done this for New York State. I didn't bring that data, but we use this model to calibrate the multiple waves of COVID in New York State. And there are all sorts of time series methods for extracting that. But maybe we should come back to that.
Yeah, sure.
But it's certainly possible to do. It's obviously not something you can directly measure, but it's something you can estimate when you calibrate the model to actual data. And we had 3 data sets for New York. We had actual mobility, we had the disease data, mobility data, which was our geocoded cell phone data for where people are, and Twitter mining of fear. And we have these guys who do sentiment analysis on Twitter. This is very, very imperfect, of course, but they're able to filter Twitter feeds for, for signals of concern, awareness, that people took action, and so on. So one way to do it is purely statistically as some sort of residual, but the other is to actually process Twitter data, social media data, and this is a very promising avenue, I think. I mean, it's very, come on, it's not physics, but it's some actual way to measure this. And actually, the person whose work you should read on it is David Broniatowski, Broniatowski, and we just finished an NSF grant that tried to calibrate these coupled contagion models to New York State data using Twitter data of this sort with some, modest statistical success. So that's how we're going about it.
Yeah, thanks. There's a couple of people in the audience who dealt with this fear stuff. So maybe after your talk, they can, ask you.
And I want to come back. I mean, this is all fear just as a parameter. When I come back to Agent Zero, I'll talk about fear as an actual cognitive process and show the equations I use that also have some actual credibility in laboratory behavioral neuroscience.
All right.
So again, parameters are always elusive, but the functional form that I really use in the agent-based model is not just these alphas and betas bulk transmission parameters. We actually embed in the agents a fear learning model. All
right.
Okay. So bad answer.
Yeah.
But,
Good.
we'll keep going. All right. And of course, so again, we can have different asymmetries because of the difference in channels, the return to the susceptible pool in one case and not the other, and so forth. And we can solve for the parameter relationship that produces fear going faster than the bug. All right. And fear obviously can stimulate social flight, which space is not included in these models. And here, Benjamin, there's all this nice, I don't know if you're familiar with J.D. Murray's work, reaction diffusion equations he developed to replicate the spread of the Black Death across Europe. But I think the PDE, generalizations of all of this work are very kind of low-hanging fruit, easy to do, and would be very revealing about spatial dynamics. Anyway, fear simulates flight, sometimes when there isn't even any disease. In Surat, India, hundreds of thousands of people fled pneumonic plague, and the World Health Organization was not able to detect any cases. They'd had a previous real plague. And again, in the behavioral epidemiology world, there is a group of economists doing what they call rational epidemics, in which people have an actual utility function that they maximize behavior subject to constraints like prevalence and cost of vaccine and all these other things. But again, I don't think fear and contagious fear are actually rational processes. And so I'm interested in different approaches where we use, neuroscience of things. Fear doesn't even need to be conscious, much less utility maximizing. So we can come, I will come back to this in connection with Agent Zero. All right, but all I want to say is that flight itself is a double-edged sword. Yes, it reduces local transmission, but it increases global spread. And we did a little toy spatial model in which people flee. And of course, not surprisingly, it spreads the disease. And we can come back to this. All right. So distancing is two-edged. Even small level of flight can amplify the epidemic spatial scale dramatically. All right. So that was the two contagion model, where there's only two contagions. One is the particulate viral transmission, and another a cognitive behavioral transmission, the fear transmission. And we extended this to a triple contagion in the more recent work with my colleagues Erez Hatman and Jen Crodell. We added another fear, fear of the control. So now there's three contagions. There's contagious disease, contagious fear of the disease, and contagious fear of the control. And in the model, we look at many different cases: contagious fear, fear of the disease, fear of the control. And of course, fear of the control, vaccine refusal, is a huge deal. The WHO counts vaccine refusal as one of the top 10 threats to global public health. And it's responsible for the resurgence of really, polio, pertussis, measles, and, COVID-19. So this is an important behavioral phenomenon, and not an entirely rational one, I would suggest. Examples are, of the fear that's not well-founded would be measles, where there's a very high R naught. I mean, R naughts are, of course, averages, but I mean, in general, it's a very contagious disease with a very high R naught of 12, meaning you have to vaccinate almost everybody to get the thing under control. And the fear of measles certainly makes sense. It can be deadly in children. The fear of the measles vaccine is not rational and has been, thoroughly rebutted. Any claims of connection between the vaccine and autism have been thoroughly, refuted scientifically. But fear of measles vaccine remains, and it's responsible for big outbreaks in 2015 in California and so on. But the dynamics now depend not just on one fear, but on two. And in general, we're interested in cycles of vigilance and complacency. One historical example of this, where there's fear of the disease, where there's real disease, smallpox, there's fear of the disease, and there's fear of the vaccine. So one of the great scourges of history, smallpox, which kills about 30% of those infected, very high case fatality rate. But even when inoculation was discovered, cycles of vigilance and complacency kept the disease alive. And Jennifer Lee Carroll has a wonderful social history of smallpox, in which she writes, in London, inoculation, that is vaccination, it's not exactly, but it's inoculation's popularity waxed and waned through the 1730s with the force of the disease, that is, with prevalence. In bad years, people flocked to be inoculated. In lighter years, the practice shrank. Inoculation was a security, the only security to cling to within the terror of an epidemic. In times of good health, however, it looked like a foolish flirtation with danger. I mean, the vaccine is a live virus, it has side effects. And again, what she's saying is that when the fear of the disease exceeded the fear of the vaccine, inoculation increased. But this suppressed the disease, and now the fear of the vaccine exceeded the fear of the disease, and the thing came back because people stopped getting vaccinated. All right, so let's think about, what's a good example? Vigilance and complacency, all right? So let's build the wrong model first, but the right idea, okay? And I try to teach my students to build the right idea first and not worry if the model's actually right. So here's a wrong model that gets the idea right, and then we'll try to build a model that's a little better, really. But let's just think of T at time T as some threat. a disease. We're obviously thinking of disease. So imagine there's some threat, and V of t is the control. This is the population, the total level of the threat and total uptake of the control, vaccine. So think of T as a disease, and V of the control, and there's fear of the threat and fear of the control. And for the moment, we're not going to let them adapt at all. We're just going to make them constants. And that, in this case, we're saying, look, if the fear of the threat exceeds the fear in equation 1 of the vaccine, then the vaccine uptake is increasing. dV dt is the difference between the fears times the level of the threat itself. All right? Really simple idea. And that the level of the threat declines the more of the vaccine people take. So let's make that as simple as possible too, just linear equations. So d threat dt is minus epsilon, a positive number, v. All right? Very simple idea, right? If the threat exceeds if the fear of the threat exceeds the fear of the vaccine uptake increases proportional to the threat. That's equation 1. In equation 2, the threat then declines in proportion to the level of vaccination. Okay? All right, so differentiating, obviously this is minus epsilon, the difference times t. And, if the threat exceeds if fear of the threat exceeds fear of the vaccine, it's Hooke's law. Simple harmonic motion, right? And the spring constant is this term, epsilon theta t minus theta v. And I'm recording sorry. So it's Hooke's law in this case, and it's exponential growth in the other case, right? And so clearly equal fears is a tipping point of this dynamics. Okay? Very simple idea, wrong model, but the right idea. The right idea is that things depend, the qualitative behavior depends on the relationship between these fears. And in one case, yes, you get oscillations, as we're interested in multiple waves and so on. All right? Now, if you add fatigue of the control, that is, this is the previous equation, minus AV, so there's some fatigue, people without the disease, they're going to give up the vaccine, then you get a spiral sink, just like you get, in the US cities, for example, in both of these cities. I mean, it's just a couple data points, but you're seeing something that goes away, as in all these cities. But it goes away as damped oscillations. It doesn't just go away. So, okay, again, very crude qualitative result, but if we add some fatigue, then we can get damped oscillations. And if you play with external forcings, a lot of people who try to get multiple waves do it by retaining the SIR simple picture and just adding a periodic forcing term, like return to school or changes in general level of congestion in the winter. And there are also biological arguments about periodicity of the vaccine's own replicative capacity. But if you throw external forcing in here without the damping, then okay, you can imagine seasonality, schools, and other things, and develop some kind of resonance catastrophic picture where the waves coincide, or at least amplify, the amplitudes are additive, something interesting, and a nice model different than all of this, and still with absolutely no behavior, is a piece by Josh Plotkin, Cy Levin, and other colleagues in PNAS. Dynamical resonance can account for seasonality of influenza epidemics, which I think is cute. But now this is all the wrong model. Okay, these are all variations on the wrong model, not Cy Levin's, but the ones I've been showing. So now let's try to get to the right model, or one that's even a little better. So I like the difference between the fears, but they need to be dynamic, of course, and change endogenously in the model. And the other problem with all of this is there's no real epidemiology at all. There's no contact between anybody and anybody else. And of course, the other problem with this is that the equilibrium is 0 and you have negative values, which is embarrassing, right, if you want to study epidemics. So there's a lot wrong with this, even though it's the right idea. So let's fix it. And this is what we tried to do in this paper in the Royal Society. And And the new model includes many coupled contagions. There's the disease itself, which we just run as a sanity test, or debugging really. And then disease plus fear of the disease, like the previous model. Then there's disease plus fear of the disease and vaccination. And there's disease, fear of the disease and vaccination and fear of vaccine. So again, we're trying to keep this as parsimonious as possible, but a certain number of new parameters are just unavoidable. So here again, we have susceptible to everything. Susceptible, SFD, is susceptible to fear of disease or vaccine. Susceptible to fear of vaccine only is this term. So it's a generalization where there's two fears, but the notation is sustained. Fear of disease, fear of vaccine, effective contact rate for fear, proportion of people vaccinated, all of this stuff. So it's as close as possible to the same notation. But now, of course, there are three betas. There's a beta for the disease, a beta for fear of the disease, and a beta for the fear of vaccine. And two mechanisms of fear decay. One is, and I'll come back to this with the Rescorla-Wagner model and Agent Zero and actual neuroscience, is fear decays when there's stimulus deprivation. If I remove the aversive stimulus or the fear-inducing phenomenon, then the fear decays. But they can also catch complacency from others. So there's a natural fear decay due to stimulus deprivation. And there's also encouragement from people who've already lost their fear, who've been in the basement and came out and said, I'm okay, and you should come out too, all right? And these useless diagrams are here. I don't understand, I never understand these diagrams. I do better with regular differential equations. And again, this is the generalization of interest. And again, we have the susceptible to disease, susceptible to infection. The SIR, the classical SIR model is these terms, beta SI, in the DSDT, I for actual infection, unsubscripted is susceptible to infection, infected with the infection, and removed from the infection. So with everything gone, no behavior, you get, again, mina beta SI, goes into the infected pool at beta SI, leaves at gamma I, and that's the removal. But what's interesting here is that we have this difference between susceptible people who are afraid of the disease and susceptible people who are afraid of the vaccine. And this is the, again, the right idea now packaged in a more mathematically acceptable way. All right? So this is the generalization here. And again, we get these vaccination cycles that depend on the balance between the fear of disease, susceptible to disease and afraid of the disease, FD, and fear of the vaccine, susceptible to disease and afraid of the vaccine. But both of those are dynamic in the course of the model. And when the first exceeds the second, people accept vaccine. But that suppresses the transmission and new cases fall. Now people become less afraid of the disease than they are of the vaccine. People refuse vaccine and the thing roars back. Smallpox is among one of these examples, but measles, polio, there's a lot of, you know, really arresting cases in which this has happened. But it's the same idea, right? And then now it's dVdt is proportional to the difference with a little bit of shenanigans, as you see in the bottom of the equation. But S, the two fears equal is a tipping point of these dynamics too, all right? And we did quite a lot of analysis and equilibrium analysis of this and so forth, which is in the supplementary material. But to show you some of the results a little more graphically, one example is what happens if fear decay is high and or low, all right? So contagious decay controls the second waves, which can actually be bigger than the first ones, which is an interesting result. In 1918, they were smaller, but in some places they were greater in COVID, for example. So if we have high decay of disease to low decay, right, high decay, people prematurely abandon distancing and they get this big second wave, and that can be even bigger than the first wave, as is true for several decay rates. If it was sufficiently high decay, you can go back to the classical picture. All right, but we get multiple waves, and interestingly, these decays depend, they dictate the timing of these peaks and the maximum and the peak itself. All right. All right. Another mechanism, of course, is adverse vaccine events. And during COVID, we had adverse reactions to one of the vaccines, and that led to the government suspending vaccinations completely. And even rare adverse events can lead to contagions of vaccine fear and refusal in multiple ways. And again, I'll come back to this, but the neuroscience of fear learning, to the extent I understand it, shows that surprise is quite important to fear. So it's quite good not to pretend that the vaccines are riskless, because if everybody believes they're riskless and there's even one adverse event, you get this giant panic. And it's the same with speculative bubbles in economics. If everybody has wild expectations and then you get one market failure, you can produce, Lehman Brothers goes under and you get this giant financial panic. And we actually have a nice new project with the Organization for Economic Development and Cooperation in Paris to use these cognitive models to study financial panics and other things. But they're all contagions of fear, really. All right, and these, again, adverse events can produce subsequent waves also. This is the adverse event rate. And again, high of adverse event rate, people abandon the vaccine and produce a very big second wave, an even bigger one than in the other case. I mean, ceteris paribus on the parameters. And lower rates also can produce second waves. And this is still possible. We're just beginning a phase of childhood vaccination in the United States, and if there's even a couple kids who do badly, my intuition is there'll be an issue, as there was with the adult vaccine. And of course, as I said before, this is a huge risk worldwide and is accountable for the resurgence of really diseases like polio, in Nigeria. People refuse vaccine because they believe vaccine is a Western attempt to vaccinate, to sterilize males, for example. Not everyone, but some. I mean, and I think worldwide, there's all sorts of suspicion of vaccines, and they produce bad health outcomes. All right, so the model generates these sorts of results as well. All right, so now we've used this term freely.